All right, welcome. So this video, I want to expand on what we've been talking about collision detection and collision handling. In the last video, we did bounding boxes and how it applied to my demo of Super Mario Brothers. But now I want to just have another quick demo of how we can use bounding circles. I haven't got an actual demo game available, so instead I created this little quick demo, which is my version of what I call robot tag, or a bunch of robots simulating the game of tag. As you can see here, the little red dot is it as it is, and the white dots will run away from it, and then the red dot will chase it. And of course, the collisions happen here whenever any dot runs into any other dot. That's circle-circle collision. Or we also bounce off the walls. And so I'm going to show you here how I've been able to implement that. So the first thing I want to draw our attention to is that I've just created a single circle class that's going to handle all of the behavior of all of my circles. And I've implemented directly into that class some collision detection. I haven't made a separate bounding circle class like I did with the bounding box class for my other demo. In this case, the circle itself is its own bounding circle, and this is actually true of how sort of the older games would do it, is there would actually be a circle built into it. That's what we draw. Well, that's the same circle for the bounding box or the bounding circle. In this case, you can see here exactly how simple the code is for our collision detection. This first method here, called collide, takes an other circle, and it does the very simple calculation that we thought. First of all, I've got a little helper function here called distance, which we can see here is just a simple Pythagoras calculator for us. That just makes things a little bit simpler. So we find the distance between the two elements, and then we check to see if that is less than the sum of their radius. That's of course the definition, or that's how we know if they are intersecting or not. And that's all I need to know. I return true if this is true and false if this is false. Otherwise, I've actually defined, hard-coded in 4 other collision methods for determining whether our circles have collided with the edges of our environment. And I've just called these collide left, right, top, and bottom. And I've got those built in with the parameters of our canvas and of the radius of our circles, so that no circle will ever be outside of the bounding region that we have, as long as we handle our collisions properly. Now I want to take a look at the circles update method, which is where I'm going to be doing most of my behavior and also all of my collision handling. So the first thing, there's a little bit of extra code here. When my circle becomes it, then I actually put a little pause in, just so that there's not an immediate tagging back of the person who tagged you. If you ever played tag when you were a child, this is sort of my version of the no tag backs rule, is I've put a 1-second pause in when you become it. So that's just that's just a little bit of extra logic there. But if you're not paused, then what are you going to do? Well, as we saw, this was also true with our physics with Mario. In Mario, I had a lot of extra logic to figure out which buttons were being pressed and so on. But after we figured out that logic, the next thing we did is we just took the velocity vector of Mario and we advanced our position by doing this dot x and this dot y in our x and our y dimension, adding on the velocity vector, but weighting it by the current clock tick, or how much time has passed since our last update. So this is advancing our position, or moving our entity based off of its velocity. And so after doing that is usually when we're going to do our collision detection. So after this, now we would normally also update our bounding box or bounding circle here. Well, as I mentioned, the circle is its own bounding circle, so I don't need to do any extra operations here. Instead, I'm going to go immediately into my collision, and I decided I was going to handle collision with the walls first. And you'll notice here I've lumped collision with the left and right walls together, and I've lumped collision with the top and bottom walls together, and that's because what we do when we collide in that way is usually going to be the same, at least in terms of the velocity. And so that's going to be the first thing that I'm going to point out here, is that when we bounce off of a wall that is aligned with our axis in some way. So there could be walls that are diagonals or on any arbitrary angle, but if we bounce off of a vertical wall, then all we have to do is change our horizontal velocity by flipping its sign. So that's all I'm doing here, is taking this dot velocity x and flipping it and making it this dot velocity x minus. I've also included this friction vector here, so if I want to include friction, that's going to slow things down when they bounce. But for the moment, and my default setting, friction is 1. So this you can ignore that for a second if you like. I do have to check to see if I'm colliding with the left or the right to offset myself. So this is part of the handling as well. In my handling, I'm doing two things. A bounce, this will change my velocity so I bounce, but this will push me out of the wall. So if I've actually run into the wall and I'm actually overlapping with the wall now, I will push myself out. And of course, that's going to be different if I hit the left or the right wall, which way I need to be pushed. The same kind of logic is going to be true for colliding with the top or the bottom wall, except we will now, since those are our horizontal axes, we will now flip our vertical velocity. So if we were moving up before, we're moving down now, and so on. Same thing with the friction. Here it's still set to 1, and then likewise we just push them out of the walls. So the collisions with the walls here are basically circle to rectangle or circle to line collisions if you like, but because the walls are axis aligned, that's going to be simpler than colliding with an arbitrary line or an arbitrary rectangle. And so you can see, well, I handle that very simply in these little blocks of code. Now the remainder here is going to be collision with the other circles. And like we did with Mario, we're going to also here with our circles iterate through all of the other entities in our game engine. All of the other entities in this case are just going to be all of the other circles. We're going to make sure, as we did before, that the current entity that we're looking at is not this entity. We're not checking to see if we've collided with ourselves. Why? Well, of course, we're always colliding with ourselves. And then if we try and handle that collision by, trying to push ourselves from, out from ourselves, whatever that means, that's impossible. So we wouldn't want to do that. So we want to skip over ourselves when we get to ourselves in the entity list. And then we'll just continue by saying if it's not ourselves, then have we collided? If we've collided, then there's some stuff that we need to do. Now, really what we're going to do here, maybe I'll add a little comment here, is the first block of code I've got here is going to cause us to push away from each other. And to do this, we might need to do a little bit of geometry or a little bit of physics. Now remember, I've got this nice distance function that I introduced that's just going to tell us the distance between our two circles. And then what I'm going to do here is I'm going to calculate this delta. Now let's see what we're doing here. This is going to take the sum of the radiuses, and then it's going to minus off the distance. So let's imagine we've got our two circles here that are collided, and then we've got this distance between them that we can measure here. Maybe I'll call it d. We also have their two radii, which maybe I'll call r1 and r2. And what we just did is we took r1 plus r2 and we minused off d. And I was calling this our difference or our delta. What that's really doing is it's saying here, look, we've got this length, that's one of my radii. I've got this length, that's my other radii. So we're adding those two together, and then we're going to subtract out this element here, which is the d. Okay, what that means is that let's just do this subtraction sort of visually here. We'll subtract out this, and we'll subtract out this, and we'll be left with this region in the middle. That difference is how much we overlap, how much we overlap the two circles. Now our goal is I'm going to push this circle away that way, and I'm going to push this circle away that way because this is the way that we overlap. So, there's more than one way we could overlap. We could overlap this way, and in this case we would want to push away here and here. So in my math, I'm going to calculate not only the distance of the overlap, but the direction of the overlap as well, whatever that might be. And then I'm going to divide that overlap in two, and I'm going to push one circle one way and the other circle the other way. So when we're done, there should be no overlap at all. We should end up with sort of a perfect touching just right at of our two tangents right at the end there. So that's what this little block of code is going to do for us. It's first going to calculate that distance, then it's going to calculate the difference, that was the delta, how much overlap there is between the two circles. These next two lines are then now going to calculate what's called a unit vector. This is going to try and figure out the direction that the overlap is in, and it's going to do this by first calculating the normal vector, which is just, we're taking the difference vector, I should say, by taking this dot x minus the entities dot x, and same thing here, this dot y minus the entity dot y. That's going to give us what's called the relative vector between the 2 points. So normally when we have two points, we would give them their x and their y coordinates, but those are relative to the origin, which again, remember in our canvas is in the top left. What we actually want when we want the direction between them is we want the relative vector, which is this vector. Instead of getting these two vectors, we want this relative vector. And the way we're going to do this is by doing an x1 minus x0 and a y1 minus y0. That gives us the relative vector. Okay. Now this relative vector has a length, a magnitude. And we don't want that magnitude, we want a unit vector. That is, we want a vector that is in a direction but has length of 1. And so the way we're going to do this is take this vector and divide it by the distance, or its length, the length of that vector. And again, if you take something of length 6 and you divide it by 6, you get something of length 1. And so that's what we're going to do here, is we've done the difference here, and then we divide out by the distance or the length of the vector. So that's going to give us our unit vector, and the diff x is going to be the distance in the x coordinate or in the x direction, and diff y will be the distance in the y coordinate, again normalized to a unit vector. Now what we do is we take the delta, that's how much we are supposed to push ourselves apart. Remember, each circle is going to get half of this delta. So we've got half of the delta here. And then we need to know how much we're pushing apart in each of the 2 dimensions, the x and the y. That's what the unit vector is telling us. Now, if we were completely overlapping only in the horizontal direction and not in the vertical direction, then our diff x would be 1 and our diff y would be 0. Vice versa, if we were completely overlapped in the vertical dimension. However, more likely than not, most of the time we're overlapping in both the x and the y dimension, and that's why we did this unit vector calculation up above here, so that we're giving the appropriate push in both directions. So for more overlapping in the x, we will push out more in the x, and likewise with the y. The other thing we've done here is we're pushing out the other entity in the other direction with the minus here. Okay, and that's important because we've calculated our direction vector in this direction. We did this dot x minus ent dot x, and that means pushing away from this object means pushing away is in the negative. So we want to push the entity away from us. So this logic is some geometry to figure out the vector that we need to push and the distance that we need to push each of our 2 circles out. After this point, our 2 circles are no longer colliding with each other, or we could say that their edges are now just touching out on each other. Now this is a simple kind of handling of nudging elements out of each other. It's not the only way to handle an overlap like this. Sometimes if you need a more sophisticated collision handling, you might run time back to before they collided and figure out when they collided, instead of, in this case, just pushing them out, handling it after the fact. Now, this is a simpler version, of course. The other thing we're going to do is we're going to swap our velocities just like we did above. When we ran into a wall, we took our x velocity and we negated it, or our y velocity and we negated it. We're going to do the same thing here, except that the laws of physics say that if you have 2 objects that crash into each other, with a few other assumptions I'm sweeping under the carpet here, they just trade off their velocities. Specifically, think of 2 billiard balls, okay, if you've ever played pool or billiards. And if you hit one ball and you've got sort of a perfect collision, you hit the ball exactly perfect, then the ball you hit will gain the velocity of the ball that hit it, and the ball that hit it will gain the velocity of the ball that was hit. Again, go practice this out a little bit if you'd like. Now this basic assumption, or this basic definition, also makes the assumption that our two objects have the same mass, and that's what I'm going to do here. So there's no mass calculations I need to make here, so I'm just doing a straightforward swap with no magnitude adjustments. The magnitude on both sides is going to be 1, and that's all I've got going on here. This is a straightforward swap using a temp variable to keep track while we're swapping. The only extra bit on there is added this little bit of friction. Remember, if you need to, just assume that this friction is 1 right now, so really we're doing nothing here except swapping our velocities. The only other logic I have here is the game of tag, which is if I'm it, then after I tag you, I'm not it and you are it. So I'm going to just put that logic in there. I've got two helper functions that just swap my variables based on whether I'm it or not. All right, so now let's just watch that in action again. We can see while they're bumping into the walls, because they are trying to run away, they tend to get clogged into these corners here. But we can see that as they bounce, watch it, some of the white ones as they bounce off each other or off of the walls when they're not sort of being chased. They bounce kind of normally like you might expect for some billiard balls. Look at these ones up here at the top here doing this sort of weird back and forth. This is a cool mathematical pattern with their rhythm of bouncing. Of course, if the red one gets over, there's something weird. But you can see that these are indeed the kind of elastic collisions that you might expect from some billiard balls. Okay. The only difference here is that they also have some acceleration built in that causes them to flee or chase depending on their role in this game. And that's something I'm just going to leave to the next video. So thanks a lot for watching, and we'll see you again in that next video.